In this video, we're going to explore Stirling engines. We'll begin with the theory, what they are and how they work. Then we'll delve into the land of experimental physics, building and running a desk-sized Stirling engine. Once we have a running engine, we will measure the operation temperatures of the hot and cold reservoirs and explore qualitatively the impact of dead volume. So first up, what is a Stirling engine? A Stirling engine is a type of heat engine. It generates work by heating and cooling a closed volume of gas by moving the gas between hot and cold temperature reservoirs. These reservoirs are air chambers with pistons that are connected to a flywheel setup. The pistons cycle 90 degrees out of phase with each other to allow the air to move around as needed to create work. The Stirling cycle is best displayed by its theoretical pressure volume diagram. The cycle has 4 thermodynamic steps as well as 2 facilitating mechanical steps. The thermodynamic steps are a constant volume heating and then an isothermal expansion, and then a constant volume cooling and an isothermal compression. Let's call Tc the temperature of the cold reservoir and Th the temperature of the hot reservoir. These 2 different temperatures are essential to making the Stirling engine work. Following along on the PV diagram, we can see that starting at point 1, we have a minimum volume of working fluid at temperature Tc, with majority of the working fluid located in the hot reservoir. Heat flows in until all working fluid has reached temperature Th, with volume staying constant and pressure increasing. This brings us to point 2. We then have an isothermal expansion at Th, and our volume increases to maximum. The next step is a mechanical and not a thermodynamic step. The momentum in the flywheel from the expansion rotates the piston a further 90 degrees, shifting the working fluid from majority in the hot reservoir to majority in the cold reservoir. This mechanical step is essential for cooling to take place and for the cycle to continue. We can now continue thermodynamically from point 3. Heat flows out of the working fluid until we reach Tc, again with volume constant and pressure decreasing. Then at point 4, we have an isothermal compression at Tc and volume decreases to a minimum. Our final step is again a mechanical shifting of working fluid from the cold reservoir to the hot reservoir, facilitated by the momentum in the flywheel. Our cycle can now begin again. Now that we know theoretically what should go on, let's build an engine and see if the theory holds up. This project started with some SCAD files that were edited, sliced, and sent to the 3D printer. Once all the parts have been printed or collected, I very quickly realized that nothing in the real world fits for free. So I drilled, and I glued, and I sanded, and I tinkered, and I screwed, and finally I assembled. With all the parts in the right place, and the engine spinning, I thought it was smooth sailing from here. But it turns out getting the engine to run is another battle. We've been having a little bit of a problem. Sometimes when I flick the wheel, this bit here comes off, and I found the solution, a nice rubber band. I did a bit of investigating on friction, and I found that this is awful. And I think one of the main problems here is that these screws are too tight. Everything became about reducing friction. Okay, moment of truth. Ooh, sweet, that is beautiful. With all these fixes in place, after trial and trial and trial, we came to this. Oh my god! Success! Now to temperature sensing. Heat engine efficiency is all about temperature difference. So I was really interested to know what sorts of temperatures I was dealing with here. I rigged up 2 K-type thermocouples to an Arduino board for my temperature sensing, one to the hot reservoir and one to the cold reservoir. Overall, I was able to approximate the temperature of the cold reservoir as 24 degrees Celsius and the temperature of the hot reservoir as 250 degrees Celsius. This gives an ideal Stirling efficiency of approximately 10%. Doesn't sound like much, right? Let's have a bit of blackboard theory here. The maximum efficiency obtainable by any heat engine is the Carnot efficiency, and for my reservoir temperatures, the Carnot efficiency gives us 43%.
Where is all my energy going? My energy is being wasted as dumped heat instead of being used as work. Losses come from friction, heat loss through connecting tubing, noise, non-ideal regeneration, and excessive dead volume. My engine may only have achieved 10% efficiency, but the cool thing about Stirling engines is that in the scenario of perfect regeneration and no dead volume, they approach Carnot efficiency. The less cool thing is that if the engine achieved the maximum efficiency, it would be doing so at such a slow pace that the power coming from it would be laughable.
What particularly interested me when looking into Stirling engines was the concept of dead volume. Dead volume is any volume occupied by the working fluid that is not altered by the movement of the pistons. I found a wonderful article deriving equations to model Stirling engine performance when considering dead volume and non-ideal regeneration. They found that dead volume will decrease the engine network and the thermal efficiency. This means that engines with large dead volumes will require more heat input and output. To scope out this theoretical work, I decided to test my engine operation with different dead volumes. To do this, I had to change the length and diameter of tubing connecting the hot and cold reservoirs. I wanted to see if I could find a dead volume large enough that my engine would not be able to supply enough heat to operate it. In the end, I managed to operate the engines with 4 different dead volumes. At our largest volume, the engine ran until it heated up so far that the glass piston actually warped, and the engine was no longer runnable. So whilst I was unable to measure the heat flowing in from my spirit burner and the heat coming out from my cold reservoir, it was interesting to find that my desk engine definitely had its limits. Large dead volumes were too much for the setup. And that concludes our introduction to Stirling engines. I hope you've enjoyed watching this as much as I've enjoyed making it.